get the most out of it. Okay, so you really need to have those prereqs. Someone asked me, am I going to just fail people that manage somehow to slip by and stay in the course? And the answer is, that's what I said at the beginning. I think I can just take you off the roster. I haven't been in this situation before. I think I can just take you off the roster, but please don't kind of put yourself in a situation where I have to fail somebody because you're not playing by the rules. Okay, so the next assignment that's coming out, you will finally get to use, some cluster computing. Okay, so there are 2 clusters that are being made available to you guys. Okay, so one is called Open Cloud. Have people gotten their invites to that yet? How many people have gotten an invite? Name of the system is called STOAT. Okay, so they should have all gone out. Okay, since the wait list hasn't settled yet. So I said earlier on, people can add, well, it's not entirely up to me, but if you're a master's student in the School of Computer Science, whether you could add late is entirely up to me and Garth Gibson, okay, who's the dean of the master's programs. And we've agreed that we'll let people do that. My experience is people drop largely before the drop add deadline, and then there's another wave of people that drop sometime around the time the first assignment is due. Okay, so if you can hang in until that point, then feel free to do so. So I went to the extra effort of getting logins for the people on the wait list as well as people that are enrolled in the class. So if you're on the wait list, you should also have an account, just so you're not starting out, behind. The other cluster is Amazon. They have this thing called the Elastic Cloud. And essentially, it's kind of like zip cars. You have to go in and register and do some computer stuff to set up credentials and so on and so forth. All right. And then when you want to use a cluster, you basically go into their system and using the web, or using a command line interface, which is what I like to do, you can basically go in and you can provision yourself a cluster. All right, for the students in this class, it'll be sort of like a moderate size thing, maybe 10 or 20 machines. Okay, and then you could do experiments on the cluster. Okay, and then when you're done, you basically turn the cluster off. You deactivate it and it goes away. Again, it takes a little bit of time to set it up. There are very clear instructions on the website. I haven't gone through them for this fall yet. So there's going to be a little bit more detail about that possibly coming out. When you're doing this, all right, so in a class this size, I'm going to say with high confidence, this is going to happen to somebody. Okay, so make sure it's not you. Okay, somebody is going to activate a cluster, start working on their assignment. And it's kind of a pain to do this. There's a latency involved. It takes like sort of 10 or 15 minutes. So think you're going out to get a rental car. You got to walk to the place and wait in line and sign something, and they give you the keys. That's kind of what's happening in a virtual world. So it'll take maybe 10 minutes for it to get set up. You'll work for a while. You'll come back. You might not want to turn it off because you're just going for a quick sandwich. Okay, and so in a class this size, somebody's going to leave that cluster going for 10 days and forget all about it. All right, and they'll get a bill from Amazon. So by the way, when you sign up for this, you have to back this up with your own credit card. Okay, so you'll get a bill from Amazon for hundreds of dollars. Okay, so this is a horrible thing. The first thing you should do is contact Amazon customer support. Okay, and so far, every time this has happened to a student, after a certain period of blind panic, okay, the Amazon people say, oh, well, you're a student, we'll be nice to you, okay, and forgive the debt, okay? So it's a hassle. You probably won't, lose your rent money, okay, but don't run into that hassle. So something that's kind of new is they're pushing people that are getting resources through this to sign up for something called AWS Educate. I signed up for it. I'm not actually sure what I get. It looks like I get discounts on some things and access to, sites designed for professors that are, getting material. I don't know what happens when you sign up. You have to give them an email. So, I think the worst case is you'll have to set up some sort of mail filter to fight off a deluge of spam. But they're asking everyone to sign up for this. I would guess probably if you sign up for this, you'll be better off. You'll be in a better position if for some reason you need to talk to customer support and get fees remitted. Okay. All right. So that's kind of the short story. So be careful. Okay. The reason we're giving you these two things is because they sort of have complementary advantages. Okay, so this is really more convenient for running small jobs. You can get to it right away. There's no setup time. There's no risk that you're going to, be charged, a pile of money because it's just a bunch of machines that are here locally at CMU that are administered by professors at CMU. They're not here to take your money except for tuition purposes. Okay, the disadvantage of that is when everybody does their assignment the night before, it will bring the cluster to its knees because it's not that large. Okay, so the actual assignment, the actual experiments you run are going to be on AWS, but this is a good way to do your debugging. Okay, questions? Okay, so we're pretty close. We've got codes for everyone in the class. We're working on a system to distribute them kind of conveniently to people, and that'll probably be out later today. Yeah, okay. It's sort of in the testing phase now. Okay, so today we're going to talk about taking stream and sort and moving from there to Hadoop. Okay, so stream and sort is basically sort of a limiting case of MapReduce when you just have one machine. All right. So again, the general case for stream and sort, we can think of it as sort of an extension of what we do in the specific example of event counting for naive Bayes. So we have a bunch of things going in. We have our logic, which generates these little updates. Okay, so these things have a key, which is the name of the event, and a value, which is the delta that you're going to add to the counts. All right. And all these messages get sorted, so so we have locality. All right, and then using that locality, we're going to scan through those messages in linear order. We have all the updates for a particular event sort of in one place, so we can just scan through that, linear time, constant space, all right, and combine all those updates easily. Okay, so that is a nice framework for doing computation if you're dealing with big files. And you have, limited memory, less memory than the data sets you've got, all right, because all of these things can be done in limited memory, okay, and if you have time, okay, so it's going to take time to stream through all this data and all this data and all this data on your one little laptop or, small desktop, okay, so what we'd like to do in general, if we've got really big data sets and we're pressed for time, is to parallelize these things, okay? So how would we do that? Okay, so it's pretty easy to see how we parallelize these steps. It's a little harder to see how we do that, but I sort of gave you some ideas. So, so what we normally have, if we kind of blow open this sorting routine, okay, is we've got our counting logic, all right? We're running this into a sort program, and under the hood it's reading in little chunks. It's breaking them up into files, which are, basically overlapping sets of keys. Okay, so these are just, the spill file will just be, say, the first, 10,000 keys in the file. That'll be the next 10,000 and so on. I'll put out these spill files, which are all sorted. Okay, then we merge all these spill files at the end of the day. Okay, and at the end, then we can combine the counter updates. Okay, so let's take this framework and ramp it up. So we're going to call this the reducer machine, and this is the counter machine. Okay, All right, so let's assume I've got 2 machines of each type. Okay, so I've got 2 counter machines, the one on the top and the one on the bottom, here on the left. And I've got 2 reducer machines. Oh, I spelled reducer wrong. Reducer or something. Yeah, okay. Here's another reducer machine on the top. Okay. So here's what we're going to do. So we're going to start out. This isn't part of the picture, but we're going to start out and we're going to take all the examples. So these are documents. And we're going to split them randomly into 2 different sets, the blue set and the red set. Okay? So this means that each one of these 2 machines only has to scan through half of the data. All right, so that's the first step in parallelizing this. Okay, now we also want to go through, and what we want to do is we want to take these spill files and arrange things so that each machine, each of the reducing machines, only has to work with a subset of those spill files. So we'd like this green machine to only use half of the spill files and the purple machine to use half of the spill files. So what we're going to do here is when we're doing this sort, which we're now going to call a partition/sort, okay, it's going to look at every event and it's going to split it into one of 2 different categories, purple or green. Okay, so it'll compute a hash code and just check the low order bits of that hash code and see whether this looks like a purple thing or a green thing. Okay, so all the purple things will be grouped together and put in one, well, let's see. We'll arrange it so that every spill file contains only purple or green keys. Okay, all right, so at each point what we're going to do, conceptually we could imagine doing this, we're going to, instead of having a single sort process, we'll have a sort process for each reduced machine. Okay, so when we get something streaming into the sort process, the first thing we do is we route it to the right sort process. Okay, then that sort process is going to construct spill files just for that one color. Okay, so that would be kind of what's under the hood here. We're splitting things up and we're doing some sort of intermediate sort. Okay, usually that's done sort of in one stage. All right, so we take these spill files and each of the machines, since it's looking at a subset of the data, right? This data is split by document ID. The counters are split by event name. Okay, so the colors have nothing to do with one another. The colors are going to change when you apply this this logic that goes through and construct events. Okay, so the colors are going to change when we basically generate the output in this left-hand part of the process. Okay, so we're going to end up, each one of these things is going to have some spill files of each color. Okay, all right, so now what we basically do is we have to take these guys, we've got to route them to the right reducing machine. Okay, so this reducing machine is going to pick up all the green ones. All right, this reducing machine is going to pick up all the purple ones. Okay, so they're going to get half the data, all right, that they normally would. And then we're just going to run the same logic to combine the counter updates. All right, now I've got a subset of the counts here and a subset of the counts there. All right, so I'm starting out with 2 splits of the data, which are called shards. I'm ending up with 2 splits of the event counts. All right, so this is how we're going to set it up. Okay, we looked at a bunch of different algorithms yesterday, Tuesday, where you can do this sort of stream and sort paradigm to do something useful. Okay, we had similar sorts of reducers. So in one case they were summing up counts. In other cases they were forming lists or forming little Gaussians over a stream of the data. Okay, but in each case they're basically doing an aggregation of all the things that are associated with a particular key. Okay, so it turns out there are lots of things that you can, or lots of algorithms you can write that are organized this way. You've got sorting, you've got streaming, you've got reduced type operations. Okay, and of course you have streaming operations that sort of convert from one object type, say like a document, to another event counts. All right, so this is the framework that Hadoop is built on. All right, so it's important to remember what Hadoop is trying to do here. Okay, so our code is not CPU bound, right? You're not using a lot of compute power to do these counter updates, or even really in the testing phase, right? The code is pretty simple, all right? The scalability issue is because we've got lots and lots of data on disk. Okay, it's I/O bound, right? What you're basically limited by is how much memory, how much data you can stream off the disks. All right. So when we want to make this faster, it's not going to help us to add more cores. Okay, what's going to help us is to add more disk drives. We want more read heads, so instead of streaming through, 100 terabytes of data on one machine, we can stream through, 100 gigabytes of data on 1,000 machines. So we want to have many, many different machines to sort of handle that streaming disk I/O. Okay. All right. So, an example of this kind of task would be, finding a particular line in a terabyte of data. All right, it's going to take you a long time to scan through and find that particular line. If you could take that terabyte and split it into 1,000 pieces and search those 1,000 pieces separately, it would be fast. Okay, so the way I like to explain Hadoop is to start off by basically backing off and just saying, well, what would I need to do if I was going to implement that? So this is a kind of a useful heuristic, I feel, for a lot of complicated systems, because you just sort of start reading about the system and you're like, oh my God, this seems so complicated. Why is it like this? Why is it like that? What's this thing? It looks like kind of a file system, but it's not quite a file system. Why is it different? So I'm just going to kind of walk you through, what would happen if someone gave you an assignment and basically said, let's just implement basically a Hadoop type MapReduce system. Okay, implement something that's going to do this sort of stream and sort operation in parallel. Okay, so this is an assignment. I actually kind of thought about doing this assignment, but I didn't. It would be a very systems-y kind of assignment, not really a machine learning-y sort of assignment. I think there are other classes that have done this. Has anyone done something like this in a class? You guys? What class was it?
214.
214? Okay. Yeah. All right. So, I mean, there's nothing intrinsically, was it a hard assignment? Yeah. Yeah, okay. So let's just kind of like step through it, okay? These guys can like sort of fill in if I'm missing something, okay? So what infrastructure do you need? So what I basically want to do is I want to do this sort of thing. So you got a stream of examples in, okay? We're running some sort of map routine, okay? It's taking these examples and it's outputting some other thing. All right, so I'm going to assume that what we're inputting is key value pairs, okay? So here we've got a document ID and then all the contents of the document, all right? And the output is another set of key value pairs, okay? Let's say, the deltas we have for an event, the key is the event name, and the delta is the value, okay? So, just to be concrete about this, we could just basically have one pair per line, just use file IO, flat files, use one pair per line and separate the key and the value with, say, a tab character, okay? So we get key values in here, we transfer them, we have another set of key values. Okay, we sort them and then what we come out is sorted key value pairs. For naive Bayes, those would be the event counts, all right? And the last thing we're going to do is aggregate them. So there's another thing which does this aggregation, right? And we talked about what that would be, okay? So this is the process, okay? So how would we break this up and do it in parallel? So here's one possibility. I'll set up several different machines, okay? So I've got 4 totally different machines that I'm going to use for this. Okay, so I've got 4 boxes. I want to split the data into different shards. So really, we want to have these shards be about the same size, about comparable in size. So we'd use a nice, well-designed hash key so we can split them into roughly equivalent sizes. Here, just to make it sort of simple, I'm just going to split things by the first letter of the document ID. Okay, so this isn't a great way of doing it, but we're going to take these documents and we're going to split them into 4 different things. All right. And I'm going to take those 4 different shards and I'm going to ship them to different boxes. So I'm not going to count this step. This is just sort of like a setup step. So I've got my data. I've partitioned into 4 sections randomly, and I put each one on a different box. Okay. So a different box means different processor, different disk drive, different read heads. Okay. So, I mean, this is a pretty simple thing. Let's just imagine I just basically have something that figures out what box I need to is going to be used for a particular key. All right, so I take everything and I send it to the right box. Okay, so the way you'd normally do this is use network I/O. So there's something called a socket, which basically looks like, a file. You can write things to a socket, and that's basically a way of transmitting data from one process on one machine to another. Okay, so we could do that. All right. The next thing we have to do is we have to run this mapper. Okay, so we've got to do something, use our little process for naive Bayes that basically would be taking the documents and producing the event count deltas. Okay, so I've got different subsets of the data on different machines, so I just run all those steps in parallel, wait for them to finish. Okay, all right. Now I've done everything, I've done those steps in parallel. Okay. And again, now this is something we can sort of do very easily, right? We put everything in some little special place on each of these 4 boxes, all right? And I'm just going to somehow invoke a process remotely on that machine, okay, that will read the input and produce the output, okay? Nothing complicated so far. All right, now I've got to take this map output and I basically have to put it into, figure out which reducer it's going to go to. All right, so I have to take this and I've got to split it up and redistribute it. All right, so here's what we can do. All right, so we've split our data, we've done our map process. And the next step is we open sockets on each box, all right, that will receive data, all right, and the way I'll set it up here is I'll just say, well, let's receive the data and basically sort of immediately run it through a sort process. Okay, so on each of these boxes, there's something which is happening on the sending side and something that's happening on the receiving side. So on the sending side, you basically open up a bunch of sockets to different reduce boxes. All right, and these might be the same boxes, they might be different ones. Okay. But we've got a socket that transmits from every mapper to every reducer, okay? And on the reduce side, when you're receiving those things, it's basically another sort process. So we get the keys that are, the right color for your reducer, okay, and only those keys, okay? So everything gets sent to one machine. We sort of have one pipe from every machine, so it's going to look kind of like this. There'll be lots of things sort of being shuffled back and forth, okay? And we're going to send it to that box, and that's going to go to some process that's going to sort things, okay? So we've now taken the map output, we redistributed it, okay? We've sorted it, all right? So now we have to run the reduce processes. We wait for the sorts to finish, okay? And we run the reduce processes in parallel. Okay, and that's basically the same thing we did before. We basically will just do we'll invoke an appropriate process for each of those reduce processes. So now I've got pretty far along here. I've taken my data, I've split it up into different shards. I've done a map for each shard. I've done this thing which is called a shuffle sort. We take the data and sort of move it to the right place because it has new keys now for reducing. All right, we've output things in the reduce process, okay? So in general, we will have to take the output of what the reduce process gives you and do another shuffle to make sure that it's on the right box, okay? So in the case we're looking at here, the keys for the reduce don't change, all right? So you do a reduce, but the keys are the same. So you get key value pairs in, key value pairs out. You have the same keys before and after you reduce, right? So you don't actually have to do this shuffling process at the end. We can just sort of leave things where they are. In general, you might have to do that. Whether you actually have to do that depends on the details of your MapReduce system. Some of them basically constrain you to kind of keep the same keys. All right, so this is the basic idea. This is what you would do. All right. Like I said, I didn't make this an assignment because it's all sort of like systems-y stuff, okay? But it's useful to kind of think about what you would need to do, all right? And it's also useful to think about like why people keep using Hadoop instead of using 100 other processes or systems that have been built by students like sort of in a few hours, because this isn't a big job, right? So what do we need? What's left to do to make this really useful? Okay, so the goal that Hadoop has is to basically, and I would also say Google's MapReduce system, right? So both of these are basically designed to use a whole bunch of very cheap machines, okay, which means unreliable machines, machines that might fail frequently, okay? They want to use a bunch of cheap machines for really large data sets, okay? So far you've looked at RCV1, which is a pretty big data set. We're going to look at one that's a little bit bigger in the next assignment, but data sets could be much, much larger than this. Okay, so if we want to take this, it's not really interesting to do it for 10 different machines, right? Where it starts to get interesting is when you're looking at, maybe several hundred machines. You're running several hundred mappers or reducers at once, okay? So that's sort of where it really sort of starts to get interesting. And then you have to run into a lot of problems, all right? So one problem is basically reliability. So what happens if one of the machines you're working on fails, either because of software problems, it's overloaded, has some sort of hardware problem, okay? And the other thing is efficiency, right? How do we deal with the details of using this, and particularly for a cluster where you've got many people using the same set of boxes, all right? And then there's like usability. It's like what other things are convenient for the user to have. Okay, so a lot of what's in Hadoop is basically there for these reasons. Okay, so let's just kind of talk through some of these things now. Okay, so this is a little picture of Hadoop. All right, so we have our data. We've got it broken into these pieces that are called shards. We have these different worker machines. Okay, in this picture, some of them are designated as map machines. Some of them are designated as reduce machines. So RPC read is basically sending things to a socket, okay? So here we'd be doing the event counting on subsets of our documents. Here we'd be summing up the counts, all right? And so these are the worker machines. Okay, these little guys are disk drives. So notice we have a lot of disk drives because that's what we're sort of trying to do. We're trying to throw lots of disk drives at a IO-bound process, all right? And then finally at the end of the day we have the output files. There's some other stuff here. We've got this job tracker, okay, that decides what worker is going to work on which problem, okay? So that's not something the user decides, that's something that's decided by the system. So let's talk a little bit about some of these issues, reliability and efficiency, okay? I'm kind of switching to a different slide deck here. So when I did this class the first time, one of my TAs was Alana Fish. So she'd worked at Google for several years, and I was sort of advertising for a student to kind of help me develop this course. And she said, oh, I'd really like to do it, but only if I get to give some of the lectures. So she was a tough negotiator, but she got her way. And this was one of the lectures that she gave. So basically, MapReduce has these three main phases. There's a map, okay, and that's basically sending the input records to a worker that's appropriate for that key. All right. There's a sort process which puts all the things of one key in one place. Okay. You never call a routine called sort. That all happens kind of behind the scenes. What you define as a map process and reduce process. The reduce process operates on each key and the set of values that are associated with it. Okay. Just as an aside, this is why I put it in gray, these come from functional programming. They're in languages that let you sort of, they come from functional programming. So here's an example of a map command in Python and a reduce command in Python. So that's where these names come from. And here again, here's sort of like a picture of what happens. We've got the shards that go to the mappers. The mappers produce data which might go to many different, each one in general is going to produce some data that's going to go to every reduce process, right? Then these things get distributed back to the reduce processes. We get a reduce, okay? I'm sorry. This is a shuffle sort, so this is grouping things into the same key together, all right? And then finally we have a reduce process. Here we just have one reduce process, so everything gets reduced together and we just have one output at the end of the day. So let's just walk through an example and that'll make things somewhat clear. Okay, so we're going to start with a corpus. This is not like a internet-sized corpus. It just has 3 examples. Okay, we're going to look at the examples. Joe likes toast. Jane likes toast with jam. Joe burnt the toast. And what we're going to do is we're going to count the number of occurrences of each of those words. So this is, for better or worse, the canonical example that everybody uses to describe MapReduce problems, the word count example. And what we're doing in naive Bayes is just this far away from word count. It's like we're taking the word count example and I projected it to the convex hull of machine learning algorithms. Okay, that's what we're doing. Okay, so we've got our input, and let's say we just shard that into 3 different pieces. Okay, so I have 3 different mappers. Each one of these things is going to compute a local count, right? So we've got, for the first one, it's got the output Joe likes and toast, and we've got ones everywhere because there's no words that appear twice in a sentence. Okay, so now what we're going to do is we're going to take that and we're going to shuffle these things together. Okay, so we've got these 3 separate input files. Okay, what we're going to do is we're going to group these things together so we have all the things with the same key together. All right, so they're only really 3 things. So there are 2 Joes, 2 likes, and 3 toasts. All right, so we have to make sure those things are grouped together. All right, and then in the reduce phase, what's going to happen is we're going to go through each one of those groups and we'll aggregate things in that group, right? So here the aggregation, we keep the key the same and we add up the counts, right? So we finally get, there are 2 occurrences of Joe and 3 occurrences of toast and 2 of likes. All right, so this is MapReduce, okay? So before I go on, right, so now I'm going to talk about replicability and reliability and so on. Are there questions? Yeah?
What's the benefit of the sort phase?
So what's the benefit of the sort phase? So you don't really need to sort for almost all the things that happen, right? Sorting is a convenient way of doing what you really need. What you really need is you need to have things that have the same key grouped together, right? You're going to aggregate the results, the values for one particular key, so they need to be together, okay? So sort is sort of a convenient way of doing that. You can imagine something where you didn't sort, but you somehow just did some grouping instead. So when you're writing a MapReduce algorithm, you should assume that things are not. You don't typically assume that things are sorted in any particular way. You just assume they're grouped together. So all the things are the same key or together. Any other questions? Okay. So so here's one of the questions. Okay. Monitoring. How do you know when every machine is done? Okay. So there's some choices you have to make. So you could have every machine, when it's doing a task, like a map task or a reduce task, when it's done, it could sort of send a message back to the master. Okay, but that's actually a little bit problematic because if a machine dies somewhere in the middle of its map task, right, maybe it's never going to get back to the master. So you think the task is just completely hung, right? And in fact, if our goal is to use 1,000 really cheap commodity machines, right, that might happen pretty often, right? If you have a large enough cluster, then failures will be pretty common. So I'm not going to do this now because my experience, so like nobody defrags disk drives, so we probably don't have a lot of hard, solid, like spinny disk drives on our laptops anymore. But when I taught this class like a couple of years ago, I asked the question, how many people basically had a hard drive fail on them in the last year? How many people have had a hard drive fail on them in the last year? Oh, 1, 2, 3, 4. Okay, so let's say 5. Okay, so we've got 150 people in the room and 5 failures. Let's call that like 2 or 3% in a year. Okay, so like ramp it up, say we've got 10,000 disk drives. How many are going to fail on any given day? It's not 0. Okay, right? It doesn't happen to you very often because you just sort of are taking care of one hard drive. Okay, but if you're taking care of 1,000 hard drives, they're going to fail all the time. Okay, so you want the software to be reliable about that. Okay, there's also like sort of a there's this Netherland where machines can be working, but not working very well. So the hard drive might have some bad sectors and it's kind of grinding away, but can sort of recover. Or the machine's really bogged down with a whole bunch of processors, right? Or there's some sort of software problem. So you've seen these before. It's a server and you can get it to answer a ping, but you can't log in, right? So it's not quite dead, but it's not at all well. So can you tell whether a machine is like dead or really slow? So, in Hadoop, basically what happens is you don't rely on reports from the machines. You basically ping them to see how the progress is progressing, okay? And when machines are slow, because we've got a big pile of cheap machines, we'll just start a backup process, okay? So, if it turns out the machine is failing, then the backup might actually finish first, even though you sort of waited a while and said, oh, that one looks slow, let's start something different. Okay. It also might be slow just because you have some compute intensive thing in your loop, or you don't realize that it's compute intensive, but on one line out of 1,000, it's going to take a long, long time. So yeah, I can remember experiences back when I was in industry where we were using regular expression matches, and they turned out to kind of bog the machine down every once in a while, because every once in a while you'd fill in a file, get a file that had single tokens that were like a megabyte long, right? And you'd be like running a regular expression inside that looking for dates or something like that. That turns out to be expensive. So sometimes the slowness is something that's completely replicable. Starting a backup process isn't going to help. You don't really know which it's going to be. But we can throw some extra processes at it. Another problem, if a disk fails, you could lose some output. Okay, so what do you do about that? Well, in Hadoop, what happens is you actually take the intermediate files, and actually everything on the file system gets replicated a few times by default. So you basically have backup copies of the data sitting on the disk somewhere else. Just now let me kind of like jump in and talk a little bit about these pieces. So what we talked about is intermediate data that might fail and having to replicate things. So, and what we also have here is we have data that's distributed, right? So it doesn't make sense. We want to split this data up, and we don't want to lose track of the fact that really it's one coherent thing. This was our original corpus. Maybe it was a single file. We split it into several different shards. We'd like to keep track of, the identity of that original object, that corpus object, right? Even though it's been physically farmed out on a whole bunch of different disk drives. Okay, so we want to somehow deal with the fact that the file system is distributed in a reasonable way. So in Hadoop, what you do is there's this thing called the Hadoop file system. All right, it's a distributed file system, okay, which means when you interact with it, it's going to feel a little bit slow, right? You'll do an ls command or the equivalent, and you'll be like, okay. So it's going to be slow because it's going out to the cluster and querying a whole bunch of machines. So when you have a sharded data, when you have a file that's been sharded, what it looks like is it looks like a directory with the shards as different files inside that directory. Okay? So it looks like you've taken your original file and turned it into a directory name, and then there are like several different things inside it. Okay? That's not really what it is. Here's a picture. Okay? So this is a little file. This is a small data set for RCV1. I copied it into the Hadoop file system and sharded it into 10 pieces. Okay, so this is the size. These are the dates. This is an old slide, obviously. All right, so it looks like it's just a directory that's got 10 different files in it, Really, it's not. Really, this is 30 files scattered all over the cluster. So there are 3 copies of each of these. That's what this number here means. Okay. I can look at any of them. So for example, there's a tail command in the Hadoop file system, as well as a -ls command. So there's a tail command, and it'll just give me the last few bytes of everything. So I can kind of go in and poke around and see what these look like. All right. And this is all sort of transparent to me. It looks like it's a directory of files. It's not. All right. Instead, this is a distributed set of 30 files. The default is you have 3 copies of each file. Okay. And when you're issuing a map task, okay, if I take these things and I say, well, I'd like to sort of like do a count on this, right? One thing that's important is this data is on at most 30 different disk drives in the cluster, right? There are a lot more than 30 different disk drives, okay? What I'd like to do, ideally, is to not move that data around more than I have to. So what would be good is if I could run the map processes on these machines, these particular machines. So what you'd like to be able to do is you'd like to run processes locally on each block. So this is part of the scheduling that goes on under the hood in Hadoop. Okay. So the last point I want to make about Hadoop, which always surprises people a little bit, this is actually a terrible waste of space. So each of these things is something like, you know, maybe a megabyte or so. Okay, and really, this is a very suboptimal way of laying out the data. So in Hadoop, what it's basically designed to do is streaming type operations in parallel. Okay, so it's optimized for streaming. Okay, now when I talked about defragging hard drives, I basically said one thing that happens if you're not careful on a normal commodity type machine is after a lot of use, the disk drive gets fragmented, so you don't have big spaces to put data in. You only have little places. So you have a whole bunch of the sort of fundamental unit. It's called a block. Usually it's something like 8K, right? And if you have an 80 megabyte file, it's going to take up 1,000 blocks, right? And in the worst case, all those blocks are scattered all over the disk drive, and you've got to seek around to find them all, to thread them together and make a single sequential file. In the best case, they're all just in one place. Okay? So Hadoop tries to optimize for streaming, and they do it in a really easy way. This is all built on top of a regular file system, and they just make the block size huge. So the blocks are typically like 64 megabytes or 128 megabytes, right? So that basically means that each one of these things here is occupying sort of a small portion of one block. All right. So it's not a bad idea to do this for experimental purposes or for demos, but if you're like storing things long term, then you want to basically reshard your data so it's basically sort of one block per shard or a couple of blocks per shard. Okay, so questions? Anything from the Hadoop experts in the front? All right, let's move on a little bit. So the other thing in this picture is the job tracker. All right, so this is not really that relevant. Let me just tell you what the job tracker is. So working with Hadoop or any cluster is not like working with a program that's running locally on your machine. Okay, so when you're debugging, you write a program, it does the wrong thing or it fails. Okay, and it's on your machine somewhere, you know exactly where it failed. So that makes it easy to go in and figure out how it failed. All right, so when you submit a job on Hadoop, what's happening is different pieces of that job is broken into a whole bunch of different processes on a whole bunch of different machines. The choice of those machines isn't up to you, okay? You know, this scheduler is making that choice, okay? It will be writing intermediate data, but you don't know where that data is, right? So that makes it a little challenging to figure out how to debug this data, this sort of process. So here's a a little bit of data, of examples, okay? So this is where I wanted to start. I just redid these snapshots with these screenshots with the new system because the UI's changed a little bit. So here I've submitted a job, okay? And when you submit a Hadoop job, there's a whole bunch of information, about what's happening, okay? So most of this you don't really care about. This is one thing you really do care about, right? It will tell you what the URL is to track the job. So this is the best way of figuring out what's going on. Let's use the job tracker, okay? So if you go to that URL, and to get there, you've got to set up, for Stoat, you've got to set up a proxy, okay? So for security reasons, there's a couple of layers that you have to do. It's not too hard. You have to set up a proxy. But then you can just go in your web browser. This is basically the status report, okay? So this finished, okay? It took 18 seconds because I was just messing around, okay? The average map time was 6 seconds. The reduce time was 1 second, all right? These are the different tasks, okay? So I can go in and click on one of these. So I can look at the map tasks, okay? So there were 5 map tasks. I had 5 map shards, all right? These are the different tasks. There's a little bit of statistics about this, the status that they actually succeeded, okay? And if I click on one of these, then I can drill in. So it might be that this was started several times, okay? So it might be that you had to start a backup task. In this case, you didn't, so there's just one task there's one attempt under this task, okay? And if I want to really see what happened, really the best place to go is to these logs, all right? So the nodes tells you something about the kind of state of that particular worker machine. The logs will tell you what happened with that particular process. Okay, so here, there's no standard error, there's no standard outputs. We just have systems logs. I'll show you, I think in a second or two, what happens when you have an error. Let's see. The other way to do is to start kind of from the top. So basically truncate that URL, the tracking URL, till you get to this thing right here. Cluster sort of gets filled in automatically on Stoat. This will give you a listing of all the jobs that are out there. Okay, so you can sort of poke around after something has finished, particularly if it's finished and failed, the job tracker URL may not work. You can go in, you can look at this thing, which I noticed it says it's finished and it's failed. So I can click in and sort of find out what's going on with it. I redid these this morning, and I hope this isn't a bad sign, but I had a discussion with the Stoat administrator, so the job tracker wasn't set up right. I'm not sure it's still set up right. It works for succeeded jobs, but this is a failed job from my last slide deck from last year. So this was a case where it was a map job. It failed. I drill in all the way through that the job tracker interface, and I pull up one example of a map job that failed. Okay, so far all the error messages I see are error messages from Hadoop, right? They're basically saying, well, something is going wrong in Hadoop, right? And it's probably my fault, okay? But I don't know really what it is that I've done until I go into the logs for the particular processes that I started up, all right? So here we've got the logs for that thing. We can look at sort of the last few things. So here, if I look at the standard error logs, and I've gone through a lot here. I've started with the job tracker URL. There'll be a whole bunch of error messages that have nothing to do with my code that have been thrown at me on the command line, okay? And once I find the error logs, then I can finally come up with some sort of error that has something to do with my code, right? So this says, well, we couldn't find a class in this package com w:/stream nb, okay? So finally, it sort of seems like, okay, there's something that I did wrong having to do with my stream naive base code, all right? So when you are debugging a Java program, this is sort of where you'll end up tracking things down. So obviously, you should do as much debugging as you can locally, because that's easier. And since there is this parallel between Hadoop and stream and sort, you can often go a long ways that way. But one of the problems with big data in real life is that your code, even if it works most of the time, there are going to be some edge cases that it doesn't work on. And you may not find those when you're testing it on small local data sets. You may not find it until you start running on a file that has 1 million lines of code, right, or 1 million examples, right? And you find out, oh, well, one example in 10,000, there are no words, right? Or all the words are stop words, and that causes an error. So those are the things that are kind of hard to find when you're testing locally. And this is sort of how you kind of have to track them down. OK, so questions? I want to do a little bit more kind of drilling into Hadoop later on. Let's talk about one way of doing this. So this makes Hadoop very close to stream and sort. So in our imaginary assignment, we basically had key value pairs 1 per line. Okay, in homework 1A, we also had things that were basically key value pairs 1 per line with a tab separating them. Okay, so Hadoop actually lets you do this. There's a streaming interface. So the mapper basically outputs a line with the key and value or a tab separated by default. Reducer reads in data in the same format. The lines are sorted just as if they were the output of sort. Okay. So that basically means you can take the code you have for algorithm for homework 1A, and you can quickly do sort of a mediocre, slightly inefficient Hadoop version of it. Okay. So here I've got 2 little programs. One basically does the event count updates. The other one does the reduce, the sum reducing. And I've got a little demo here of what you could do. So if I want to run this locally, I basically can take my event counting program, all right, and what I can do. Let's see, what am I doing here? Oh, this is the training phase, I think. Yeah, we take the training data, we run it through this thing which constructs the deltas. All right, we sort it. This basically says I just want to sort on the key field, the first value. All right, and then I run it through the reducer, and this gives me the total counts of all the events. All right, and then I have another little program here. Okay, so this program, if you give it some extra arguments like the test file, okay, and the set of things you want to look at, and I guess this was for smoothing maybe, then you can read in the event file, and it will do the right thing. Okay, so this basically is the test algorithm that I talked about the other day. All right, so it does this, and then at the end of the day, it's just sort of reporting some overall statistics on its performance. Okay, so just to back things up a little bit, this assumes I've got data. Okay, if I want to take this and I want to run the same sort of code on Hadoop, all right, I have to figure out a couple of different things. So first thing I have to do is I have to take my data and split it. All right, I have to shard it. Okay, so one easy way of sharding data is again using the streaming interface. So to run a streaming job, the syntax is this. So generally, when you're running your own code, you say Hadoop jar, and then you give the name of your jar file. All right, that will have your code in it. All right, so here we're using a different jar file. All right, we're using one that's this streaming Hadoop extension. Okay, so in Hadoop, typically it will throw an error if you try and overwrite an existing data file. That's kind of its default. So I'm going to start by clearing the space that I use for output. All right, then I'm going to run the streaming jar file. It has a couple of arguments. So the input and the output are where the input and output are going to be. And the mapper and reducer are basically shell commands that do what you want, right? So this is a shell command that you can use to map the documents to events, deltas, and this is the shell command you use to map the event deltas to aggregates, okay? And the other thing you have to do is you basically have to tell it how to do these things. So remember, these things are going to be executed remotely on worker jobs, on worker nodes, okay? So this naive Bayes.jar is a jar file that's got my Java code, all right? It's on my local machine, but it's not on the worker machines, right? So to tell it there's a file that the worker machines are going to need, you have to put this little extra command in here. So this says first upload all this naive Bayes.jar file to all the workers, all right? Then I do a MapReduce with this input and that output, okay? And finally, we know how many map jobs to run because we're going to start off with 1 per shard, okay? We don't specify how many, we need to specify how many reduce tasks to run, okay? So this will be the number of output shards you have. All right, so this is how we can run this sort of code on Hadoop streaming. And here's just a little log of doing it. So I basically typed in this make command, so it's executing this Hadoop command. You can sort of see what happens. There's a whole bunch of stuff about the internals of Hadoop. It tells me what the job tracking URL is. This is old. And then it starts giving me status. So it tells me how the map tasks are doing. So eventually they'll finish. The reduce tasks can't really start until the map tasks are over, but they can start doing some sorting and partitioning. So there'll be a little bit of reduce action before the map tasks finish, but not very much. After the map tasks finish, then the reduce tasks start. All right. So this is giving me this update every so often. Or I could go to the tracking URL and watch sort of a prettier version. Okay, all right. So this is what we're going to do. So to split things into shards, I can also use the streaming command. Actually, the Hadoop streaming is actually very useful in a lot of different contexts. But so to interact with the file system, we use the Hadoop fs command. All right. So if I type in, help here, it'll give me a list of what the commands are. Most of them are pretty obvious if you are used to Unix commands. Let's see if there's anything else that's actually, so one that's a little different is get merge, which will take data and sort of unshard it. So you get sort of a single file. Yeah, so this is that same little thing I mentioned. Okay. So one way to shard text is you can first use the put command to upload it to the Hadoop file system. All right. Then you can run a streaming job that where all the operations are sort of null operations. Use cat as the mapper and cat as the reducer. Okay. So the only thing that basically happens is a shuffle sort, and then you specify the number of shards you want by specifying the number of reduced tasks. So that's basically how you'd get the sharded data to start with. The other thing you need to do before you run that Hadoop command is you need to put your code in a package that can be uploaded to all the worker machines. So here I've got a little make target that will create a naive Bayes.jar command that I can then invoke. Let's see, where was it? Here, okay. So this is Java. I'm specifying the class path and the main routine. And that's sort of what I need to do is sort of in terms of preparation for running streaming Hadoop. Okay. So are there questions? Yeah.
Are we supposed to use the Hadoop when we test the model? And all we will need to use for training, so we use the code for testing?
So the assignment, you're going to use Hadoop for both testing and training, but you're going to do sort of the simplified version of the test where you're using a small test file, okay? What will be big is the event counts, all right? So the event counts will be the output of a map process. It will be a big sharded file. okay? So that's sort of the large input to the reducer. Okay, so I broke this up, last year I broke this up into like one more assignment. So last year what I did was I basically had you do the stream and sort thing, okay? Then I had you do like a Hadoop streaming version, okay? Which is very easy. It's basically just making friends with Hadoop, getting your cluster set up and so on and so forth, okay? And you can use exactly the same code in the same way if you understand what you're doing, okay? There's a disadvantage of streaming, okay? In fact, there's several different disadvantages of streaming. So one thing is you don't have any opportunity to do any type checking. The things you're working with are always strings. So when you start working on a complex MapReduce process, it's easy to sort of have the logic wrong, have the wrong assumptions about what the data looks like, okay? And it's better if you're passing around Java objects rather than strings, okay? That also means you don't have to like parse strings and reparse strings, okay? Strings are not very compact, right? So basically the problem is you don't really have a lot of control over how your messages are laid out. That's also an efficiency problem, okay? So when you're really looking at optimizing I/O costs, which is really what we're trying to do, right? We have an I/O bound process. We're parallelizing so we can make the I/O faster, okay? Then putting myself in a situation where I have very limited control over what the messages look like is probably not a good start, okay? So Hadoop streaming is a convenient way of prototyping things, but it's not a good way of working with code if you want it to be efficient. So if you want to write more efficient and sort of like type checked kind of real Hadoop code, then you need to go sort of beyond the streaming level and look at what the actual Java API is for Hadoop. So here are some examples of this, and this is like the canonical word count example. All of you should probably take a look at this on your own. Here's the main program that would get run. So this is sort of the equivalent of typing in that top level command or running it in a make target the way I did, okay? So first we set up something called a configuration, which will tell you some basic information, tells Hadoop some basic information about where to contact the scheduler and so on and so forth. Normally you don't need to give that any arguments. Okay, then you create a job which relies on that configuration, and this is just a name for the job. It will appear in the job tracker. Then you basically need to tell it what the mapper and reducer are. So we're doing it here. Okay, we're specifying what the class is for the mapper and reducer. And then you have to figure out what it is that is the input and the output. Okay, so the input and output here are specified here. So we've got text as input and text as output. All right. And then we're also specifying what the keys and values are. Okay. So this is basically how that data is going to be encoded on disk. So it's going to be encoded in sort of text format. This is basically telling you what's the structure of those key value pairs. All right. So you might think that those key value pairs might be something, if we're doing like, word count, a U-based counting, the key might be a string and the output might be an int, right? But that would be too easy, okay? Instead, everything, all the kind of primitive types in Java are wrapped by special Hadoop versions. So text is the Hadoop version of a string. Int writable is the Hadoop wrapper around an int, okay? And then finally, we have to say what the inputs and outputs are, right? So this is another way of this is the way you configure the job to do that. And then finally, you want to run the job. So there are different commands for the job. This one basically runs it and then blocks until it completes. So when you execute this, it's going to sort of wait until you finish. So if you want to do a workflow, you could have a couple of things like this, set up a couple of different jobs that maybe one job feeds into the next job. So let's drill in a little. Are people clear about this? Make sense? Questions? So I'm going to drill into what the mapper and reducer would look like. Okay. So we're going to set up a class here. Okay. And what we have here is we have a key value input and a key value output. Okay. So input key, input value, input key, input value. All right. So we're starting off, we're just reading a corpus. All right. That's what this text input format says to do. Okay. And in that particular format, you really just have a value, right? I mean, so I propose we have a document ID and then a value. But in the Hadoop format, basically all there really is a value. So the key is something relatively arbitrary. I think it's the byte offset into the file. So you have a key that you're going to ignore, and then you have a value, which is a string, or in Hadoop words, a text. Okay. This stuff is just summary. Okay. So we've got a constant 1 here. We've got a place to put our output. Okay. And here's the loop. So the main routine in a mapper is map. Okay. It takes a key, a value, and something called a context. Okay. A context is like the file handle. It's like your standard output. Right. This is how you interact with sort of the outside world. Okay. So we basically take the value, which is text, all right, and we turn it into a string. It's almost a string anyway, all right. Then I'm going to tokenize it and go through the tokens one by one. So this is just standard Java stuff, okay. And I'm going to set this word object to be the value of the next token, and then I'll write out, using the context, basically that word and the constant 1. Okay, so that's what the mapper does. It generates all these word one partial counts. All right, and here's what the reduce does. Okay, here again, what we have is we've got a key value. All right, so this is the format of the key, this is the format of the value, and this is what you're going to output. Okay, so these are the inputs and those are the outputs. But there's actually a little bit of work. So in our Hadoop streaming things, we had all this little logic where we kind of kept track of the last key so we could figure where a run started and ended. All right, so Hadoop is going to do that for us behind the scenes. So we get a key and we get something that will iterate over the values. Okay, so iterate over them doesn't mean they're necessarily put in memory. Okay, so this is doing the equivalent of reading those values one by one from a line. Okay, you shouldn't assume that these are all going to be stored in memory because that could lead to efficiency problems. Okay, in general, all you can do is iterate over them. So you basically go through the values one by one. Here, all I'm going to do is basically add up the values. Okay. All right. So this is basically doing the sum reduce, and then when I'm done, I write out the new key and the new value. Okay. In Google's MapReduce system, there's a very similar API, but you don't write out the key. The key just is the same as your input key. Okay. So this is the actual Java API for Hadoop. So we're going to ask you to do that for the next homework. Yeah, question?
In this reduce example, is the value that's given, is that always going to be 1 just because the map is the way it is?
Yeah, in this case, all the values are always going to be 1, unless you use a combiner, which we'll talk about in a second, right? Yeah, here there'd always be 1. So let's just talk a little bit about some of the issues, okay? So MapReduce is not hard, Okay, sometimes it's hard to break algorithms into MapReduce steps. All right, so that's a particular kind of algorithm design. We'll work through a bunch of examples over the next few days. You guys will do some things that are a little bit more complicated, but that's sort of the hard part. There's some things to keep in mind. Okay, when you see things coming in a reduced stream, okay, you can iterate over those things. You don't know what order they're going to be in. Okay, you can impose some ordering on those things by sort of going further into the API, but by default you don't have any order control over that order. All right, so you shouldn't really assume that. Okay, you also shouldn't assume anything about the order that the different workers are going to work in. So they could happen in any order. They might happen more than once if they're backup processes. Okay, all you can really assume is that the values for the one key are together in the reducer, and the reducers always start after all the mappers finish. Okay, that's the only thing you really know. Okay, when you're running these things, every time you do a map, every time you would do a reduce, that's potentially on a different machine. Okay. There are some other API calls, so you can set something up. You can run an init phase before a sequence of maps, and you can do sort of a shutdown phase after you've done a bunch of maps. But in general, and this is the kind of the key thing which will be different when you're testing it locally versus when you're running it on the cluster. Okay, they'll be running on different machines. They'll be running in different memory spaces, different JVMs. Okay, so there's some things that you can do in real Java when you're running locally. So if you want to communicate, between two different processes, you can set up a static variable, right? Okay, that is not going to work here, right? It'll work when you're running it locally, and then it'll fail when you're running it. It'll just behave differently when you're running it in distributed fashion. Okay, so just keep in mind, you're running these things in sort of little chunks on a cluster that you have relatively little control over it. So sometimes in a complicated algorithm, you might be tempted to say, well, I want to actually communicate between two different mappers or two different reducers. I want to have mappers kind of talk to each other and say, well, are you doing something with like a similar key or something like that? Hadoop doesn't make this easy. Probably you shouldn't be doing that, right? If you're trying to run things on a Hadoop system, it's certainly not, something for beginners to do. That's basically sort of, using pliers on the problem. Generally, you're not supposed to know that, right? They try and hide that from you, and sort of communicating across things in the cluster any way other than sort of MapReduce is a bad idea. Okay, so if you're having trouble fitting things into a MapReduce, it might be that it's just not a MapReduce problem. Not everything is. Okay, so really MapReduce is for things that are based on streaming type operations. Okay, and if what you're having isn't something you can decompose into a bunch of streaming operations, maybe Hadoop is not the optimal way of doing it. So we'll talk a little bit about other paradigms later. And again, this is not hard. Okay, how many people have finished assignment 1A? Good. Okay, so you've basically done MapReduce at this point. Okay, if you run stream and sort, you've basically done a MapReduce. All right, all that's left is sort of the details. Oh, and this is something that I mentioned this earlier. Okay, in reduce, you iterate through the values. This is equivalent to in your stream and sort routine. You basically have a little buffer that's just sort of keeping track of like a running sum, or appending the values or something like that. And you're going through things line by line, and you're only storing a little bit in memory at one time. Okay, so usually you don't want to put all the values into memory. Okay, that's unless you know for sure that there's like some a priori bound on how big the reduced values are going to be. That's usually a bad idea. Okay. Questions? All right. I got one more topic. I'll talk about it quickly now, and I'll talk about it in a little bit more detail next week, I guess. So some of what we do is a little bit wasteful. We had a clever question down at the end where someone said, well, are all the counters going to be 1 when we read them in? I could just have the sum be like plus equals 1, right? We could do this. But let's also think for a second. One thing we're doing here we'd like to do is we'd like to reduce the amount of disk space that we're using. We want to reduce the size of the messages, particularly messages that get sent from one machine to another. Okay? So that's slow. Okay? So the reducers can't start till all the mappers are done and the data in its partition has been sorted. So just like before we had sort of a bottleneck, the size of the events that get sorted is sort of the limiting factor in how fast the whole MapReduce, the whole stream and sort pipeline runs. Okay, we get the same sort of thing here. It's often the case that in MapReduce, basically the shuffle sort is a substantial part of the time. Okay, and we saw that we could optimize that. We could improve that a lot. Okay, I don't know what's a factor of like 3 or 4 here, just on this simple small example, by doing some of the aggregation locally. Right? So rather than doing a map and a reduce, we do a map and we kind of reduce. We sum things up as much as we can until we sort of start running out of room, right? So we do some of the aggregation locally, all right? So in Hadoop, you can do the same thing. The thing you use is called a combiner, okay? So it sits between the map and the shuffle. So it takes the output of the map, all right, and it does some local reduction on a subset of what's going to go to the reducers. Okay, and if you're lucky, that will make the data smaller, so you don't have to send as much stuff over the network. Okay, now there's a trick to this. It only works for some operations. So what happens is you'll take some random subset of the things for a key, and you'll basically run this combine operation, which is like a reduce operation on those. All right, and then you'll take the results of those, subsets that you've reduced. And you'll be doing a further reduce operation on those at the reduce phase. All right, so things happen in 2 phases. You have absolutely no control over what subset of things happens in the first phase. So the order can't matter. Okay, so here is the code for a combiner you could use for word count. All right, it is exactly the same as the code you use for a reducer if you let the sum be the sum increment be incremented by the value, right here, rather than just increment by 1. Okay, so this basically means we're going to keep a running sum, and then that running sum sort of becomes the kind of like new partial sum, and then we'll combine the new those partial sums in the reduce phase. All right, so often you can use the same class for the reducer and the combiner, but not always. So that's basically it. And no, I guess I didn't show, but basically there's sort of like one extra line. You specify a mapper class, a reducer class, and also a combiner class. Okay, so that's it for today. We'll see you guys next week.